biofuels, and we had seen a basic introduction to what biofuels are and all the generations of biofuels and all these other things that we had discussed. Now we are going to start from there. So the first part of our lecture today will finish off this portion of biofuels, and then we'll move on to our second segment, and the second segment is about nuclear energy. So this is basically how we are going to discuss, we are going to go about today's class. Now, first and foremost, to start with, we are talking about bioethanol. Now we discussed that there are three major types of biofuels: bioethanol, biodiesel, and biogas. So biodiesel is something that we had discussed in yesterday's class, and we begin with bioethanol as the second part. Now bioethanol is pretty similar to how the structure of or how petrol works. So that's why what we have seen is that mixing bioethanol in petrol is possible, and that is basically precisely what we are trying to do in India and across the world. You'll see that something similar is being tried, that we are trying to replace a portion of petrol and mix bioethanol instead. So for example, in India, the target that we have kept is a 20-80 ratio, meaning that 80% will be petrol and 20% will mix bioethanol in it. So that is basically what we want in this kind of a scenario. Now, when it comes to bioethanol, obviously it also comes with its own advantages, and advantages are pretty similar to the advantages that we saw for biodiesel as well. So for example, we see that it can reduce carbon monoxide by up to 30%. It can reduce VOCs or volatile organic compounds by up to 50%, nitrogen oxides by up to 35%. Then apart from that, obviously it also reduces carbon dioxide emissions also, and there also we see that up to 40% reduction can also happen in carbon dioxide emission. So overall, again coming to sulfur dioxide also, because it contains no sulfur, that's why there is no sulfur dioxide emission. So in this manner, we see that there are all these things that we understand about bioethanol. Now overall, when it comes to bioethanol, that is basically what we know. And overall, it can reduce, just remember we are talking about can, all right, it can reduce greenhouse gas emissions by up to 85%. Always be very clear about the words. We are not saying that these are the exact numbers. We are saying that in ideal case scenario, this could be up to 85%. The emission reduction can be up to 85%. Similarly, we are saying that carbon monoxide also can be reduced by up to 30%. Similarly, even carbon dioxide, we are saying up to 40%. Always remember this. We are not specifying this as an exact number. All right. So that's why we see that there are all these things with regards to bioethanol, and it is supposed to become a very, very important part of our economy, and it will help in reducing our dependency on imports. And we shall discuss about all these at a later stage today. The third is biogas. Now, biogas, the main component of biogas is methane. The main component of biogas is methane, and methane, by almost, you can say almost up to 85% methane. All right, it's up to 85% methane, and that's why biogas, we see that more or less it's methane, plus there are some of the other gases as well. For example, there could be carbon dioxide, there could be other gases, but methane and carbon dioxide largely make up for almost 99% of the composition of biogas. Rest 1% could be nitrogen oxides, even oxygen, even elemental nitrogen, hydrogen sulfide. All these kind of gases could be present in the rest 1%. So that's why that's a very trace amount to even count. So almost 99% would be just methane and carbon dioxide. Now, when it comes to biogas, typically this is something that is produced by the breakdown of organic matter in the absence of oxygen. Right, in the absence of oxygen, or you can see in a manner in a limited supply of oxygen. we ensure that it's not a simple area, let's say an open area like this, where you have ample amount of oxygen available. We'll try to do this decomposition, make this decomposition happen inside a closed jar, inside a closed chamber, so that there is no amount of oxygen or extra oxygen that can penetrate through. And hence, in a limited supply of oxygen, or in a very minimum supply of oxygen, we try to ensure that this biogas production happens. So that's why we say that it happens by anaerobic digestion with the help of anaerobic bacteria of biodegradable material such as manure, sewage, all the wastes, etc. So this is basically what biogas is. So if you look at this particular picture, this is how the formation happens, that we will collect all the waste, all the organic waste, whether it is plant-based waste or animal-based waste. So we'll first pick all this waste, and all this waste will go into an anaerobic digester. So that's why anaerobic. Anaerobic means what? What is the meaning of anaerobic? Anaerobic, what is anaerobic? Without oxygen, right? In the absence of oxygen. So in the absence of oxygen. So that's why it is an aerobic digester. Now in this, the decomposition of all this organic matter will happen, and the gases will be emitted from here. And this is what constitutes biogas. This is what will constitute biogas. And now this can be collected from here, and we can use it either as domestic fuel if you want, and even for electricity production also. So in any way that we want to use this energy, we can do that. All right. So that's basically what biogas basically does. Now, whatever is left over, one more thing that is important for you to understand, that we are collecting biogas from here. Now the decomposition that has happened, the leftover after the decomposition, even that is something that is useful, because it is organic in nature and rich with all the organic matter, and that's why it can also be used as biofertilizers. So that's why the leftover uh, organic material, the leftover waste material in a manner, it goes out as biofertilizer, while we also get biogas from this kind of a plant. Now setting up this kind of a plant is not that difficult. All right, setting up this plant is not that difficult, and that's why we see that it can be done at a very local area as well. I mean, at a very localized stage it can be done. Similarly, if we want, we can also make a big plant or make a big production plant out of it. Even that, doing that is possible. So that's why we see that there are n number of ways in which we are using it. So primarily, as we discussed, that you have methane, carbon dioxide, and small amounts of hydrogen sulfide, moisture, or even oxygen, nitrogen oxides, etc. So all these can also be present, but as I told you, that methane plus carbon dioxide makes up plus for almost 99% of biogas, right? So now what happens is that it can be, the production can happen at a very small scale also, the production can happen at a very large scale also. Production can happen even for, let's say, a local community or even a household for that matter. And at the same time, the production can also be done for a very you can create a very big commercial plant also out of it, and that is basically what we also call as bio CNG. That is what also becomes bio CNG. So if you've heard of bio CNG, bio CNG is also a part of our national biofuel policy. There also bio CNG has been mentioned. So this bio CNG is nothing but very similar to what biogas is, just that the production is happening at a fairly large scale. All right. So wherever we are doing this very large scale production of biogas, in a manner we have been using a different nomenclature for that, and that nomenclature is bio CNG. All right. So that's basically what we see with bio CNG. So the gases could be all these, and they basically can be used as biogas. Now, in case of biogas, bio CNG, when I'm just writing it here, This is nothing but large scale production of biogas. All right, large scale production of biogas. Whereas the other term, which is popularly used in India, is gobar gas. So gobar gas, in a manner, you can say, is a small scale production. So in India, popularly, these are called as gobar gas plants. So gobar, because that's basically cow dung. So because cow dung can be a big source of biogas production, that's why these have been named as gobar gas plants. So that's why we see that there are all these nomenclatures that are used. Essentially, they are all nothing but biogas. Now, when it comes to biogas, one thing that must also be noted is a major advantage that biogas gives us. Now, apart from obviously the fact that it is renewable, it is cleaner source of energy, it is easily available, production is easy, there are all these things. It can lead to employment generation. So basically, all the advantages that we saw with solar energy, wind energy, geothermal energy, many of those things obviously hold true in case of biogas or biofuels in general also. But there is one very important advantage that we should always understand with regards to biogas, and how it has a positive impact in checking climate change or checking global warming. Just understand how. Now, when we talk about global warming, you'll obviously go into the details in environment and ecology class, but we know that the majority, the big reason for global warming is what? All the greenhouse gases. Can you name greenhouse gases? It's not a new topic. I know that in environment and ecology you are again going to discuss it. Yes, carbon dioxide, methane, correct. What else? Nitrogen oxides, ozone, water vapor, correct. Chlorofluorocarbons, hydrofluorocarbons, yes. So all of these are called as greenhouse gases. Why greenhouse gases? Because they have something called as the greenhouse effect. What is greenhouse effect, if you can tell me? What is the meaning of greenhouse effect? What is the meaning of greenhouse effect? Trapping of the heat, correct. Hmm. Trapping of the heat, not necessarily trapping of the heat of the sun always, all right? Trapping of heat. Yeah, so that for us the major source is sunlight, but any kind of heat, if you can trap and you can use that, then in that case it's greenhouse effect. So even for example, let's say we know that our atmosphere is responsible for greenhouse effect on the earth, so that the moderate temperatures on the earth can be maintained, and that's why we are able to survive. If there was no oxygen, sorry, if there was no atmosphere, the heat trapping on the earth wouldn't happen, and all the heat that we are receiving from the sun would also be released back. So that's why then in that case the temperatures would be very extreme and we wouldn't survive. So greenhouse effect is not a bad thing. It's not that it's only bad, it's also good because it leads to our survival on this earth. But excess, I mean, it goes without saying, and there's a uh, everybody would have told you this, that excess of everything is bad, and that is what's happening with greenhouse effect. That the greenhouse effect that's happening right now is more than what is a permissible level for survival of organisms on the earth, because the amount of greenhouse gas emission has drastically increased on the earth because of various industrial activities and various production and manufacturing activities, due to transportation, use of coal, petroleum, natural gas, etc. So because of all that, we see that there has been a significant increase in the greenhouse gas emissions. Because of that, the amount of greenhouse gases in our atmosphere is more. Because of that, the heat trapping on the earth is also more, and that's why the average temperature on the earth has been increasing, which is very bad. Even if it increases by 0.1 degree Celsius, even then it is bad. So that's why it's not that you would think that, okay, fine, what's the difference between a 30 degree Celsius temperature and a 31 degree Celsius temperature? For you, practically, it might not seem anything. But when we say that the average temperature of the entire globe has changed or has increased, that has a significant impact, because it's an average taken from all across the globe, and that's something which is very, very dangerous. So that's why, from that perspective, what we see is that when it comes to the greenhouse gases, excess of greenhouse gases is very bad. Now, among the greenhouse gases, the biggest problem right now for us is carbon dioxide, right? It is carbon dioxide, because carbon dioxide is being produced or emitted in the largest volume, right? In the largest volume. So that's why carbon dioxide is the biggest menace. But at the same time, and I'm still trying to just summarize everything. You will go into the details in your environment and ecology subject. Carbon dioxide has become a major challenge for us because of the volume in which we are producing carbon dioxide. But if, let's say, if it goes to the potency of greenhouse gases, or how harmful all the greenhouse gases are, methane as a greenhouse gas is more harmful, way more harmful actually, as compared to carbon dioxide. But the thing with carbon dioxide is that it is produced in very, very large volume, and that's not the case with methane. But if, let's say, the choice is between 100 grams of methane and 100 grams of carbon dioxide, 100 grams of carbon dioxide is way less harmful as compared to 100 grams of methane. So 100 grams of methane will be much more dangerous for me as compared to 100 grams of carbon dioxide. Just that the sheer volume of carbon dioxide that we emit today is very, very high as compared to any other greenhouse gas. So that's the reason why uh, carbon dioxide has become the bigger problem. But now understand something. We are talking about biogas, and in case of biogas, what we are saying is that biogas emission, or rather biogas production, is happening from plant and animal waste, and cow dung is a big part of it, or any, let's say, animal waste is a big part of it. Now when it comes to cow dung, it's not that we need to make the decomposition of cow dung happen. Naturally, also, cow dung decomposes very quickly. I mean, if, let's say, there's cow dung somewhere lying on the side of the road, uh, you might have observed that within like 7 to 10 days, it would completely disintegrate, completely decompose, because of the action of the decomposers and the microbes. You'll see that it completely decomposes. Have you seen it? That how fast the decomposition happens for cow dung? Yes. I hope that you are not among the ones who are going and observing it as it happens. So, but what we know is that the decomposition happens very quickly, right? Now, when this decomposition happens, this is where methane is released. All right, this decomposition releases methane. Now, this methane will simply go and mix with the atmosphere. So, this natural decomposition increases the methane quantity in the atmosphere. So, if the same cow dung, instead of me just looking at it and looking at it decompose, if I collect it and take it to a biogas plant and let it decompose in a biogas plant, then in that case, we'll see that this methane will not be released into the atmosphere, but rather this methane will be trapped as uh, biogas, right? It will be used as biogas. This is where production will happen from. So in a manner, we'll be able to reduce our emission of methane if biogas production can happen efficiently. So that is one major advantage that biogas production all across the world can give, because we somewhere have to offset the number or offset the amount of emission that we are doing, right? We are doing a lot of emission, and naturally, I mean, if we were not adding extra methane, then this natural amount of uh, methane that is going as decomposition of animal manure would not be a big problem. because it's a part of the natural phenomena on the earth, so it wouldn't be a big challenge for us. But because we are adding extra amount of methane into the atmosphere, we also need to somewhere offset that extra amount, and this is one of the ways in which we can offset that extra amount. So that's why methane based biogas production becomes very very crucial from that perspective also. So that's why that is one of the advantages that we also have to think of, right? So for example, if you see, nitrogen dioxide can warm the atmosphere by up to 300 times more than carbon dioxide, and methane at least up to 25 times more than carbon dioxide. So that is the reason why we don't want these to just emit, just to go and mix with the atmosphere. And that is where we see that biogas can play a major role in offsetting that extra biogas quantity. Now, coming to a very, very crucial point, and this is about the national policy on biofuel of 2018. Now, in 2018, there was a new policy on biofuel that was suggested by the government of India, that was brought forward by the government of India. Now, before this, there was a 2009 policy as well, but the 2009 policy did not succeed pretty much. I mean, most of the targets that they had kept, most of the things that they had said in the policy did not materialize by even 10% or 20%. So that's why it was not a good success by any stretch of imagination, the 2009 policy. But then we also understood that biofuel policy becomes very very crucial, and the basic problem with the 2009 policy was that there were a lot of targets, but there was no proper roadmap to achieve those targets, right? So for everything you need that if you have the target to crack this examination, there is a roadmap that you have to do that, correct? You have made strategies around that, that how you'll complete, in what time you'll complete, how you'll write the tests, how you'll revise. So there is a entire roadmap around it so that you can get to your target. So there one of the criticism says that although we had the targets in place, we did not have proper roadmaps in place that could help in achieving these targets. So that's why this was one of the major problems with the 2009 policy. Now 2018 policy tries to mend its ways and tries to ensure that this time there is a roadway, um, there is a roadmap, there is a proper strategy that we have so that we can achieve the required goals. So if you see, as a part of national biofuel policy, the major objective is that there should be 20% blending of ethanol in petrol and 5% blending of biodiesel in diesel, and this is to be achieved by 2025. Now initially in 2018 the target year was kept to be 2030, that these targets of 20% blending of bioethanol and 5% blending of biodiesel, it should be achieved by 2030. But then there was an amendment that was made in 2021, and then in this amendment they brought down this target year from 2030 to 2025. And that's a very aggressive target setting, because just 4 years before the target year you are saying that now we are revising the target and we are decreasing the timeline, we are shortening the timeline to achieve these targets. So these are very bold steps in a manner, but we have seen that there are a lot of things that are being done to ensure that we reach these required targets. So the so that is why we see that there was a reduction that was done, and this was the 2021 amendment to the 2018 policy, right? Now what we see with regards to the targets of biofuels, we know that the 2022 target was 10 gigawatt, correct? 2022 target was 10 gigawatt, and we were able to reach 10.7 gigawatt, correct? 10.7 gigawatt we were able to achieve. The next target that the government has kept is for 2030, and the 2030 target is 30 gigawatt. So it's a very steep target, right? It's a very steep target, because you just, if you look at percentage perspective, you will say that we are adding 20 to 10, meaning that we are talking about a 200% increase in the target, in the revision of the target that we have done. So that's why this is not going to be very easy task for the government to achieve. But we see that there are a lot of policies and there are a lot of programs that they are running parallelly to ensure that they can increase the installed capacity as quickly as possible and as much as possible. So now, when it comes to the 2018 biofuel policy, there are certain aspects of this policy that becomes very crucial. First, for example, is the categorization that has been done for the first time. That this categorization basically is into the first, second, and third generation. So for the first time, we see that this kind of categorization has been done even in India, that all the different types of biofuels and all the different types of resources, they all have been divided into various generations, so that we can also customize it, and we can also see it, and uh, get to the targets, or even keep our targets accordingly. So that's why we see that from that perspective, this categorization is a very welcome step. Similarly, the scope of raw material has been defined, meaning what kind of raw material we are allowed to use, that also has been defined this time. So, for example, they have talked about, they have defined starch based. Starch based raw material. Similarly, sugar based raw material have been defined. So starch based meaning the ones that have good amount of carbohydrates in them. So for example, corn can be taken as an example. All right. Then sugar based meaning the ones that are good, obviously good sugar sources. So sugarcane juice is one such example. Then after that, they also have defined wastes. So wastes could be two types, obviously. One could be municipal waste, and then agricultural waste. So agricultural waste could be anything. It could be the leftover of the crops. It could be the damaged grains. It could be anything that will not be sellable in the market, rotten vegetables. All these things actually come as agricultural waste. So, for example, uh, broken rice has been defined. Broken rice, crop residue. Then at the same time, interestingly, rotten potato was also mentioned. Rotten potato. Now, obviously, potato directly we don't want to use, correct? We don't want to use potato directly because potato is probably the most staple vegetable in our country. Every part of the country, in one form or the other, we are consuming potato, correct? So that's why if potato is directly allowed to be used, then the prices of potato will rise, and that's not good, right? So that will lead to overall inflation because potato is being used everywhere in any one form, correct? So that's where rotten potato, they mentioned rotten potato here. So that's why all these are agricultural waste. So rotten potatoes, now instead of going into our food, into the samosas and the dosas, it will go into the biofuel production plants, right? So that is where we see that all these are also welcome steps in a manner. Then, apart from that, there is one more thing that has been mentioned, and that is, sorry, used cooking oil. used cooking oil. Now, in case of used cooking oil, when we say used cooking oil, has one problem. If you know about this, that if you heat the same oil 3 or 4 times over and over again, then that oil is not usable anymore, and that is not good for health. If the same oil has been used multiple times, then the chemical structure changes and the amount of fats, or especially trans fats, in that oil increases. So that's not good for consumption. But uh, many a times you don't even know. I mean, for example, if you're going out to eat in a restaurant, you're not even asking. I don't think you go there and you check what kind of oil is being used, whether they're using the same oil that has been already overheated multiple number of times or not. You simply go, you order, you eat, and you come back. So that is basically where we need to understand that these are also some of the issues that we have. And to address this, I mean, in a manner to address this health concern, we see that now used cooking oil, the government is saying that there will be agencies, and there are agencies all across the district which could collect the used cooking oil. They can collect the used cooking oil, and they would pay some amount of money for that also. So that's why, so that the hotels, etc., they don't have to use the same oil over and over again, and they can simply just give it out to all these agencies, and these agencies will provide it to the all the different kinds of biofuel production plants, etc., that we have. So whether it is ethanol or biodiesel, especially for biodiesel, this becomes very, very crucial, because in biodiesel production, all this used cooking oil will be very, very important and very useful. So that is basically, we see that used cooking oil also becomes very, very crucial. Then apart from, so that basically helps, obviously. Then apart from that, we see there is something else too, and this is the scenario of bumper crop. Do you know about what bumper crops is? What is bumper crop? What is the scenario of bumper crop? Surplus production, correct. Surplus production, right? So whenever there is surplus production, there is one problem in economy. You might come to know about this, that when the production is very low, the farmer obviously loses, because the production is very low, so that's why they don't earn enough. When the production is very good, when the production is much more than what's actually required, even then the farmer loses, because then their produce loses the market value, and there's nobody who's ready to buy all that surplus. So many times the farmers also, they don't have any other option but to just throw that crop away. You'll see that this keeps on happening from time to time. So this is where the government says that whatever is the surplus, that surplus can be bought by the government. Surplus will be bought by the government, and that can become a source of extra income for the farmers also. So that is what has actually been uh, pres- has been suggested by the government, and that's why all these things, it has been included as a part of the scope of the raw materials. All right, all these become a part of the raw material. So this is basically what we see, and that's why this definition is very, very important, because now that they have pretty much defined that all these things can be used as uh, a source for biofuel production, this will this will help a lot. So bumper crops basically are nothing but the surplus production. The surplus production is called as the bumper crops. So that is where we are talking about the product protection to farmers, because farmers will also gain from here, because there is an extra income source that the farmers are getting. So that's why for it's a production, it's a protection for them whenever these kind of scenarios arrive. So that's why it helps a lot in these kind of scenarios. Then so this is basically related to the surplus. Then after that, there is something called as the viability gap funding. Now, in case of viability gap funding, this is a scheme of the government where whenever there is any part, let's say any scheme or any policy of the government that needs extra investment in any form, whether it is through tax rebates, whether it is through providing extra budget, whether it is through providing subsidies, whatever be the manner. So, in any manner, if they have to provide certain extra amount of financial help, then that is called as viability gap funding. So basically meaning that whatever you need to make that project viable, to make that project work, for that extra support, viability gap funding is a method. It's a provision that the government of India has kept. So this viability gap funding as a provision also has been kept for biofuel policy, in especially in biodiesel production. Especially in biodiesel production, this is something that has been kept. And then to boost biodiesel production. So biodiesel production in any manner we want to enhance, and that's why farmers will be provided with extra incentives for that. Viability gap funding will be used here, and we are trying to increase the scope of the raw material through which the production can happen. So we are trying to do all that to ensure that especially biodiesel production can be improved, especially the second generation biodiesel production can be improved. So that's why there are all these things that we are also trying to uh, take as a part of this policy. So that's why there are n number of uh, benefits that we are looking at with regards to this policy. For example, reducing the import dependency is one of the things. So for example, the data that was brought forward by the government while they announced the new biofuel policy, they said that if let's say there is 1 crore liters of E10 fuel. E10 basically meaning 10%. I'll write it here itself. E10 means wherever there is 10% ethanol. 10% ethanol. So that's why it is called as E10. So in case of 1 crore liters of E10 production, it saves almost 28 rupees 28 crores in forex reserves. All right, so which is a big amount. And overall, let's say in 1 year the production can be up to 200 crore liters. 200 crore liters. So just you multiply this number by 200, that if the production is 200 crore liters, then it means that we are talking about 5600 crore rupees worth of forex that can be saved in 1 year. So that's why this is a big amount that we are talking about, in case, because ultimately why are we saying that it will reduce our import dependency? Because now instead of using 100% petrol, you'll be using 90% petrol, or we have a target of using just 80% petrol. So you have to use 20% less petrol. So obviously your import will also reduce, and that's why our forex reserves can increase. So that's why this is a very, very important point. Then apart from that, it obviously can lead to cleaner environment as well. So for example, again, if we take the same 1 crore liters of E10, if we have this 1 crore liters of E10 can save around 20,000 tons, 20,000 tons of carbon dioxide, right? So which is a big amount. So again, just imagine that if we are talking about 200 crore liters production in a given year, then this number, when you multiply by 200, just imagine the kind of uh, uh, reduction in carbon dioxide emission that we are looking at. So that's why this also becomes a major, major advantage from the perspective of the environment. Then after that, obviously health benefits. So health benefits first in terms of pollution, because there will be lesser pollution, less pollution. And also from the perspective of the used cooking oil. From that perspective also, we are looking at certain health benefits. Then apart from that, municipal solid waste management is also something that will get the help, because a lot of fuel production will happen from these wastes, so that's why these wastes can be useful there. Then apart from that, it will also lead to infrastructural investment in the rural areas. So especially, for example, uh, when we are setting up a plant, all right, so let's say if we are setting up a plant, there is one plant that has a capacity of 100 kiloliters per day. If it has a capacity of 100 kiloliters, 100 kiloliters per day, so if it has a total production value of 100 kiloliters per day, then it can lead to up to rupees 8,000 crore investments. It can lead to rupees 8,000 crores investment in these kind of areas, which is a very big amount. Similarly, we see that there are all these biodiesel plants, etc., which are being uh, uh, set up in India, and that basically leads to a lot of these investments in the rural areas also, because it's not that we cannot set up so we can set up only in the urban areas. We can select any area that we want, and especially the investment that will happen in rural areas, it will also help in the uh, up in the rural economy, or in the betterment of the rural economy. It will help boost the rural economy and the per capita income in these kind of areas. So that's why from that perspective, it's a very very important factor uh, when it comes to it. Similarly, when we talk about the employment generation, we see that the estimates of the government says that if there is only uh, plant one plant that has a capacity of 100 kiloliters per day, one plant with capacity of 100 kiloliters per day will be able to generate up to 1200 opportunities or 1200 jobs. So that is why from this perspective also, this will be a major boost to economy. And then finally, additional income to the farmers, because whether it is about agricultural waste, whether it is about the second generation biodiesel production especially, we see that for all these things, or even for the surplus crops, for all these things we'll see that the farmers will be able to get some additional income. So that's why for them it will be very very crucial. So additional income will come in various ways. It can come from agricultural waste, from surplus crops, from biodiesel based crops. So in all these cases, they will get the help, or they will be able to generate extra income for themselves. So that's why there are all these different kinds of benefits that we are expecting when it comes to all these kind of scenarios. Now, there are multiple such schemes that the government is running. For example, one scheme that has been often in the news is the Pradhan Mantri Jeevan Yojana. Now, as a part of this scheme, what we basically see is that this is something that will help in providing financial support to bioethanol projects. And total outlay of the scheme that they have kept is almost 2000 crores for the entire 5-year plan that they have between 2018-19 to 2023-24. So we'll see that all these kind of areas are being set up, and they are trying to set up all these aspects so that we can boost the total amount of production that we have, both for bioethanol as well as for biodiesel. All right, so from that both the perspectives, we see that this is something that becomes very crucial. Now, lastly, there is one issue which we also need to address with regards to where when it comes to biofuels, and this largely it is with regards to our food. Is the audio and video clear? I had some issues with my All good? Okay. Because my screen blacked out for some reason, so that's why I was worried. Okay. So now here we have to understand something. What I told you yesterday is that although we have first, second, third, and fourth generations of biofuel, we are largely dependent still on the first generation biofuel. Second generation, third generation biofuel, or especially third generation biofuel, is still nowhere to be seen. Second generation, still we see that some production is happening, and the government is also trying to boost it, provide it with as much money as possible, and all that. But still, the production largely is still dependent on the first generation. And first generation, as we all know, is dependent on food crops, that you are using corn, you are using soya bean, you are using sugar cane, you are using even rice or potato or any carbohydrate based vegetables or fruits, etc., can be used. So that's why ultimately we see that it is competing with the food, it is competing with the food that we consume. So that becomes a crucial challenge, and that's what we need to understand from this perspective, that production of genetically modified crops will be encouraged. This is something that we need to understand, and because of that we might not see a very good uh, nutritional value in the crops that are being produced. Because ultimately what will happen is, if you read this with along with this particular point, that increase in demand for fuel crops will lead to lower food quality and diversity, because we will largely try to enhance the production in terms of quantity and not the quality, right? So quality may degrade but quantity may increase. So that's not good for our nutrition. Our nutrition would need a good quality, will need good nutrition, and that is where we might falter. So that's one major problem that we need to understand. At the same time, the food import capacity, especially of the poorer countries, will decrease, because just understand this, their demand is always going to be constant, correct? Many of the poor countries, they do not they are not capable enough to produce enough food for their population, so they are dependent on imports, and maybe many of these countries are not even in conducive areas for agricultural production. So that's why they are dependent on other countries from Europe, in USA, even India, China. All these countries have been exporting food to these countries. Now what happens, their demand remains constant, but our supply may decrease, because we might want that instead of exporting this food, why not use it for biofuel production? So a country may think like this, that let's use this surplus for biofuel production instead of shipping it out of the country and exporting it to some country. So that's why what's happening here is that the demand remains constant, the supply is decreasing, so obviously the prices will rise. So that's why their import capacity will decrease, because they are poor countries, we are already defining them as poor countries. So it's not that it's easy for them to get this extra amount of money and keep paying for all the imports of the food. So that can become a major challenge for many of these countries also. So that's why this is something that we need to understand, that why exactly are we saying that food import capacity for many of the countries might decrease. So in this particular scenario, what we are saying is that demand remains constant, supply decreases, so price increases. Similarly, what we know is that the food prices in general can also rise, because here also what's happening is that your supply is remaining constant, correct? The supply remains constant, but the demand now has increased, because you want to use the same crop for food also, and you want to use the same crop as biofuel is also. So that's why the demand has increased, because there are two sectors which are looking for the same crop, and the production hasn't. Production has remained fairly constant. So in second scenario, what's happening is that the supply is constant, demand increases, hence the prices will also increase. So that's another scenario that we are looking at. Then the third scenario, the food and fuel crops will compete for land and water resources, because you want production. Any company or any government, let's say, wants production, so for that they need land. Land is not available, land is scarce, so prices of land rises, prices of getting water will rise. It's not easy to get that water, so that's why ultimately this will also lead to price rise. This will also lead to price rise. So we see that there are all these possibilities, and calling them possibilities probably is wrong today, because in Europe especially, there was a study that was done, and they found that even if you adjust for inflation, even then you will see that there has been at least 10 to 15% rise in prices of rise in the prices uh, of all these crops that are used as biofuel also. So in Europe already there is a 10 to 15% price rise because of biofuel, and that is something that will happen everywhere else, including probably India also. So that also becomes a big challenge for us. And then lastly, water availability for human consumption will also be threatened. Now, many of these crops, especially that we are using for biofuel production, they are also water intensive crops. Can you name a couple of them? Which are the crops which use the most amount of water? Yes, rice, sugar cane, two of the most problematic crops from that perspective, right? So, paddy, basically. So, paddy, sugarcane. So, these two, especially, we know that they consume a lot of water. They need a lot of water to grow. So, and both of them, we know that both of them actually can be used for biofuel production, correct? Both of them can be used for biofuel production. So, that is why even more problem with regards to water will arise, as if we do not start stepping away from first generation biofuel. That's why we see that there is uh, so much of efforts that are being made by the government to ensure that they can move towards second generation as quickly as possible, so that we don't have to keep depending on all these crop or the food crops largely. So that's one issue that we also need to address. Look at this question. This question was asked in your 2018 paper. Supporting this industry. First, production of algae based biofuel is possible in seas only and not on continents. Why not on continents? What we discussed is that algae grows underwater. This can be any water. So underwater means not only seas, but even lakes, ponds, etc. Wherever you have static water, wherever you have stagnant water, in those kind of scenarios, in those kind of areas, you can grow algae. So that's why algae is not supposedly to be grown only in the seas. So anyway, only is an extreme word. We have a rule for extreme words, right? So that's why this is wrong. That it's not only seas, but also it can happen anywhere. Then setting up and engineering the algae-based biofuel production requires high level of expertise or technology until the construction is completed. That's true. We discussed that the technology requirement is very complex, and that's one of the precise reasons why it has been so difficult, not only for the developing countries, but even for the developed countries to start using algae-based biofuel. So that's why this is correct. Economically viable production necessitates the setting up of large scale facilities which may raise ecological and social concerns. This also is true, because ultimately, if you start setting up in industries around algae, then you need to grow algae. And if you are trying to grow algae artificially in any, let's say, aquatic ecosystem, then you are also going to harm that aquatic ecosystem. You are going to change that aquatic ecosystem, and that may not be good for all the other species that are growing, all the other plant and animal species that are growing in that ecosystem. So that's why it will raise ecological concerns for sure. So that's why we know that that's why you can say in a manner both these statements, statement number 2 and 3, are correct. right? So this is about our first part, that is biofuel. If you have any questions, please let me know, and then let's move forward. Any question from whatever we have discussed until now? This other, and you might know about Bharat stages that India uses, or the Euro stages that Europe, etc., use. So in all these, slowly and steadily, we have been adopting the technology that is suitable for these kind of changes. So that's why these modifications can run along with these newer generation engines that we have. Broken rice basically is, I mean, as the word tells you, it's the broken rice, and usually does not sell in the market well, because otherwise, I mean, it will not have the same value as a good polished rice has. So that basically is what we call as broken rice, because it does not have value in the market, it is sold very cheap, and that's not good for the farmer, and hence the government can use it. I'm not sure if you are change will decrease, right? You have 80 carbon atoms, let's say, that has been broken down into 10 carbon atoms per chain. So now there are 8 chains of 10 carbon atoms each. So number of chains has increased, the number of atoms of carbon per chain has decreased. Once the plant plant is completely set up, that is something that we generally assume. So basically, take you back here. So setting up and engineering the algae based biofuel production requires high level of expertise and technology until the construction is completed. So that basically we are talking about the setting up until, so read it from here. Because we are talking about setting up, so obviously until it is completed, it is going to be a lot of expertise and technology required. And at the same time, because you need a lot of engineering, you need a lot of people, manpower, that also needs a lot of investment. So that is why for a developing country especially, it becomes a huge task, because for them it's not going to be easy to manage all those funds and invest so much for your completion of the project. And we see that many of these compounds that we have, the volatile organic compounds, they can be very harmful from the perspective of uh, the environment. I mean, you'll see that they lead to a lot of air pollution. The indoor air pollution also is something that they can cause. At the same time, they can also lead to uh, things like climate change. They can also be a contributor to. So there are multiple ways in which they can be very harmful, and that's why volatile organic compounds, they actually can be very dangerous, and that's why we mentioned it there. So something like, for example, benzene, toluene, etc., they all can be taken as volatile organic compounds. Currently 20% mixed with petrol, we are trying to reach there. I mean, there are some parts of the country where already we have been able to reach 20% blending of petrol with blending of ethanol with petrol. Other places we are at 10%, and we are trying to increase it to 20. Reduce the pollution issue across the capital. It's something that one of the major problems has been that the state governments also have to be involved here a lot, and it largely has to be facilitated from the point of view of the state governments, so that the central government can also step in and use that. But unfortunately, we see that uh, ground reality is not um, close to the ideal case scenario that we should have seen by now. Because last 2 3 years also, it's not that the things have improved. We have seen the recent scenario again, something similar happening in Delhi and across the areas. So still, at ground level, uh, the things haven't fared as good as they should have been. And here the involvement of state governments actually becomes very, very crucial. Do we receive carbon credits for any renewable energy? I mean, as a company, yes, companies can do that. Companies actually have been doing at an individual level. No. Is it required all the data to be remembered for examination? Some of these data can be very, very important, because see, this data especially, it's not that they will ask you this data. It's not that in prelims they will ask you this data. This is a data, or these kind of data sets, they can be useful when you write a mains answer, when you write an answer, when you're writing an essay. These are the cases where it can actually become important for you, or this is where you can enhance the quality of your answer. Instead of writing generalized answers, if you start writing answers with keywords, with data examples, it enhances the quality of your answer, and that is where all this data will be useful. Prelims, it's not that they are going to ask you this data, they'll never ask you this data. Green fuel, nothing but any fuel that is clean is called as green fuel. Renewable fuels, for example. All right. So I think I've taken most of the questions. So let's move on to the next part of our discussion, and this is about nuclear energy. Now, the discussion of nuclear energy will be divided into two parts. The first part will be about nuclear science, and second part will be nuclear technology. So, first part, called as nuclear science, is where we'll try to understand the basics with regards to nuclear energy. We'll try to understand where is this energy coming from. So, all these aspects of the basics related to nuclear energy is the first part of our discussion. And in the second part of discussion, we'll discuss about nuclear technology, where we'll discuss nuclear reactors and India's nuclear program, the applications of nuclear technology, and so on. So those kind of things will be nuclear technology, the second part, and the first part is nuclear science, the basics of nuclear technology. Now, second part, let me tell you this, that the second part will be easier compared to the first part. So first part, something that we are beginning now, is not an easy portion. So I need your concentration here. If you have any doubts, you're most welcome to ask those questions, and we'll take those questions during the break. But I need your concentration here, because this can be a little difficult part compared to many of the other things that we have been learning. So first and foremost, nuclear energy. Now, when we say nuclear energy, the meaning is what? The word nuclear is coming from where? From the nucleus, correct? This is a word that is coming from the nucleus, and that's why the energy that we are deriving from inside the nucleus of an atom will be called as nuclear energy. So that is why it is called as nuclear energy. So nuclear energy, what we can see is that this is energy. When we say nuclear energy is what? This is energy derived from inside the nucleus of an atom. All right. So that's why it is called as nuclear energy. Now, so when we are saying nucleus, let's also try to understand what we mean by nucleus. So let me just draw a picture and show you instead of these diagrams. So here what you see is that you have electrons, protons, and neutrons, etc., and all these are a part of the atom. Now, to understand what the atom is, first and foremost, what we understand is that, let's say, if we assume this to be an atom, if let's say this is an atom, then inside the atom there is a very small portion, there's a very small space. This is called as the nucleus. This small space is called as the nucleus of an atom. All right, this is called as the nucleus, basically placed somewhere at the center of this atom, and very, very small as compared to the atom. Very small. I mean, it's not, this diagram does not tell you the exact proportion of what the actual ratio could be. The actual ratio could be something like this, that if you imagine a classroom which can hold almost 100 students, if that classroom is the atom, then you just think of the nib of your pen, and that perhaps could be the nucleus inside this atom. So that could be the kind of difference between the size of the atom versus the size of nucleus. All right. So you have very small part inside this atom, which is called as the nucleus. Now inside the nucleus we have two parts, or two types of particles rather. There are two types of particles inside the nucleus, and these basically are protons and neutrons. So inside the nucleus we have protons and neutrons. Inside the nucleus we have protons and neutrons. Now in case of protons and neutrons, you might notice that protons carry positive charge and neutrons do not carry any charge, correct? So protons and neutrons actually are protons. So if you, for example, if you see this, yeah, so if you see this, you have protons here, you have electrons, and along with these protons, these red colored parts, this you can say that these are the neutrons. All right, these are the neutrons. So this is how we have. So this is a very small scale nucleus, and inside the nucleus you have the neutrons. So in this manner we see that this is where we have all these present. So overall what happens is that from the nucleus we are getting the nuclear energy, and this nucleus is at the center. Now overall what happens is that outside this nucleus you have various orbits. You have various orbits, and all these orbits, you have various orbits like these, right? So we have all these different orbits, and all these orbits is where we have all the electrons. So electrons will be present in all these orbits in a defined number. All right, so electrons will be present in orbits. So this is a typical structure of an atom. So atom basically will have all the orbits, where in all these orbits you have electrons, and inside you have this very small nucleus, and inside the nucleus you have all these protons and neutrons. So in this manner we see that this is basically how we are looking at the things. So overall we see that this is basically how we are looking at the structure of an atom. Now this nucleus that we have inside this nucleus that we have inside this atom, this is where we see that you have all these protons and neutrons. Now what we know is that electrons have negative charge, protons have positive charge, and neutrons have they do not have any charge, they are neutral. That's why this is being derived from there. Now have I made a spelling mistake? Oh, I have missed the C. Sorry. All right. So now when we are talking about uh, the nucleus, basically what we are saying is that this nucleus has protons and neutrons. Now protons are positively charged, correct? And you might know this, and something that is taught in your lower classes a lot, that like charges repel and unlike charges attract. Correct? Like charges repel and unlike charges attract. So this is basically what happens here as well, that obviously all the protons, they have been kept in a very small space, so they have a lot of repulsion along among them. But the nucleus actually are able to nucleus is able to hold all these protons with a very strong force. So if you remember, we discussed something called as the strong nuclear force, right? We discussed something called as the strong nuclear force. So that strong nuclear force basically is the force with which the nucleus is able to hold all the protons and neutrons together, irrespective of their electrical charge, irrespective of the force of repulsion. It is able to overcome all of that, because strong nuclear force, as the name suggests, is strong. So because it's a strong nuclear force, it is stronger than the electromagnetic force, and that's why it will be able to hold all the protons and neutrons together, even though there is a force of repulsion along among all these protons here. So still it will be able to overcome all that, because just imagine that it's a very small space and it is still able to hold everything together. Now, so that is basically what we see. Now overall, when we are looking at the structure of atom, what we see is that we knew about electrons way before we knew about protons, and we knew about protons before we knew about neutrons. So first electrons were discovered, that there are negatively charged particles, and they were named as electrons. And then later on protons were also discovered, and as positively charged particles, and they were named as protons. Anyone who knows the names, just give me the names. Who discovered electrons? Who discovered protons? Who discovered neutrons? Once it is J.J. Thomson. Then protons. Protons, we most of the times we attribute it to Rutherford, but there is one name that we should not forget, that is Goldstein. I'll tell you why. And neutrons is James Chadwick. Now, so in case of electrons and neutrons, it's fine, there is just one name. But for protons, I've mentioned two names for a reason. That if it is about the specific discovery of the charged particles inside the atom, it's Rutherford. Because Rutherford is the one, he was the one who basically had given this structure, that you have a very small space inside this atom, and this is where uh, all the protons or all the positively charged particles should be placed, and most of the atom is empty, according to Rutherford. So in a manner, he was the one who actually had defined the presence of protons inside the atom. But almost 20 years before him, there was Goldstein, and Goldstein for the first time had shown charged particles. Because until now, the belief was, or the model for atoms said, that there are negatively charged particles, but there is no positively charged particle. So, for example, when J.J. Thomson, when he discovered electrons, the model of atom that he had given was pretty much like a watermelon. That how in watermelon you have that reddish color area, and in that reddish color area you have all the embedded seeds, right? So these seeds basically are electrons, and all the reddish colored part is the positively charged sphere, according to that model. So that's why there were no particles of protons as per the initial models. But then that changed, because Goldstein proved that there are particles which are positively charged. He did not name it as protons, he did not say anything, he just said that there are positively charged particles also. But then after that, it was Rutherford who, through his model of atom, he showed that inside the atom there is a very small space called as the nucleus, where you have all the positively charged particles placed. Yet there were no neutrons that he defined. So neutrons are something that came later, and this was James Chadwick. Now, uh, in a manner, when it comes to the discovery of neutrons, it is also attributed to our understanding of isotopes, our understanding of something called as isotopes. Now, when we talk about isotopes, just understand what isotopes mean. If you look at the picture that we have right here, now, do you know what is isotope? Can you tell me first before me going forward and telling you? Systems, different mass number. All right. So atoms of the same element with same atomic number and different mass number. What is atomic number and what is mass number? This is all class ninth chemistry. If you remember, you remember. If you don't, I'll tell you. What is atomic number and what is mass number? No problem if you don't remember. Don't be bothered if you don't remember. That's fine. So atomic number is equal to the number of protons. Atomic number is the number of protons, and mass number is number of protons plus neutrons, right? So number of protons is atomic number of protons plus number of neutrons is mass number. Always remember, because many of you wrote it here, always remember, never define atomic number as the number of electrons. Never do that. Although we say that the number of protons and number of electrons in any given atom is the same, but we never define atomic number as the number of electrons. The reason is it's easy for an atom to lose or gain an electron. For example, many particles are called as charged particles, positively charged particles or negatively charged particles. So when something is positively charged, it does not mean that it has an extra proton. It means that it has lost an electron. So that's why electrons are lesser in number, protons are uh, the same number that they were, but electrons are less. So that's why this particle has become positively charged. And similarly, when any matter, if it gains an extra electron, then in that case the number of electrons is higher than the number of protons, which remains fixed. So that's why number of protons does not change. Number of protons does not change. Number of electrons, on the other hand, can change. So that's why we don't define atomic number as number of electrons. We always define it as number of protons. Now always remember that number of protons is the most important property of any given element. It basically defines the element. If you change the number of protons, you essentially change the element itself. The reason is it's very, very, very difficult for any atom to lose or gain a proton. All right, it cannot. In normal circumstances, it cannot lose or gain a proton. It might be able to lose or gain an electron. It may be able to lose or gain neutrons, but protons are the most difficult to gain or lose. They'll keep sitting inside the nucleus and just be there and rest there. They'll never come out of the nucleus, and they are never even bothered about entering the nucleus from outside. All right, so that's why that's the most important property of any element. It basically, you can say, it defines the element. All right, it defines the element. So anyway, so overall, when it comes to the discovery of neutrons, it is attributed to our understanding of the isotopes. So isotopes, what we are saying, atoms of the same element with same atomic number but different mass number. So now when we say same atomic number, means number of protons will remain the same. Different mass number meaning that the number of protons plus number of neutrons, that quantity changes. So if you look at this figure that we have for hydrogen, So you have hydrogen with mass number 1, mass number 2, and mass number 3. Now if you see in the first one, so in the first one, can you tell me how many protons and how many neutrons do we have? When you see this hydrogen one, how many protons and how many neutrons? It has one proton, it does not have any neutron. What about this? Here you have mass number 2. So how many protons and how many neutrons? 1 and 1, correct. 1 proton and 1 neutron, that's why the mass number is 2. And here you have mass number as 3. So how many protons and how many neutrons in the third case? 1 and 2, correct. 1 proton, 2 neutrons. So do you see that number of protons remains the same, number of neutrons change, correct? So that is what hydrogen is. Hydrogen has 1 proton. If you have 2 protons, then it is not hydrogen anymore, it is helium, correct? It will change into helium if you have an extra proton. So that's why what we see is that it will keep on changing like that, correct? From 1 to 2 to 3 to 4 to 5, if you keep on going, then in that case you'll see that even the element keeps on changing, right? The element will change. You have hydrogen, then you have helium, then you will have uh, lithium, beryllium, and so on. You'll keep on moving forward. So then you'll have boron, then carbon will come, and then nitrogen will come, and then oxygen comes. So in all these cases, you'll see that it will just keep on increasing. So element keeps on changing as you increase the number of protons. But that doesn't happen. That doesn't happen with number of neutrons or number of electrons changing. It may not change the element itself. So that is basically, you can say that this basically led to the discovery of neutron, that you have 3 forms of hydrogen. How should that be possible? Because every hydrogen will have 1 proton and 1 electron, right? It's a neutral atom, so it has 1 proton and 1 electron, yet the masses are different. That one, there is this hydrogen 1, which is lighter, then you have deuterium, which is heavier, and then you have tritium, that is even more heavy. So that is basically what we see in case of uh, isotopes. So these isotopes, in a manner, you can say, led to the discovery of neutrons. Because if you see, mass of a proton 1.67 into 10 to the power of minus 27 kg, mass of an electron 9.1 into 10 to the power of minus 31 kg, mass of a neutron 1.67 10 to the power of minus 27 kg. So if you see, mass of a proton and mass of a neutron, they are very similar, right? They're very similar. So that is why when the ratio of the masses of hydrogen is in the ratio of 1 is to 2 is to 3, this is what led to more observations and more studies, and ultimately they understood that that extra mass that is coming in hydrogen, it is coming from another kind of particle that we had not seen yet, and this is a neutron. And why neutron? Because uh, it is neutral, that's why the name that was given was neutron. So until now, this is what we know. I mean, to put things in a very in just maybe 1 or 2 sentences, what we know is that we have an atom, and inside the atom you have a nucleus which has protons and neutrons, and this becomes the source of nuclear energy. How does it become the source of nuclear energy is the next thing. So we have this mass energy, the concept of mass energy. And this concept of mass energy comes from a very famous equation. I'm sure that many of you already have heard of this equation. I'm not saying that you need to know what equation is. Whether you know or not, you've heard it, right? You've heard that there is something called as E is equal to mc squared. And this is an equation that was given by Albert Einstein. Now, the significance of this equation. Until now, the scientists did not know that mass and energy, they are interconvertible. That mass and energy actually can be converted into one another is something that we never knew of. So until now, it was either mass or it was energy. So we did not know that all these, I mean, both of them basically are interconvertible. But this is something that changed when Einstein basically showed that mass is another form of energy, or can be seen as another form of energy, in his relativity concept, or theory of special relativity, special theory of relativity. Relativity is more related to energy, and this is where he had given this equation. So E here basically denotes energy, right? E is energy, M is mass, and C is speed of light. So he gave this equation and he showed that there is a way in which energy can be converted into mass. Now this became very, very crucial, because there was something until now which was called as mass defect. Now understand the concept of mass defect. So let's say you have one nucleus, and inside this nucleus we have one proton. Let's say there is one proton, and let's say that there is one neutron. All right, that we have a nucleus, and inside the nucleus I have one proton and one neutron. Now this proton, let's say, is of 10 grams. The weight of proton is 10 grams, and the weight of neutron is also 10 grams. Then in that case, the weight or the mass of the nucleus should be 20 grams, right? If you have just one proton and one neutron, the mass of the neutron should be 20 grams. But what the scientists observed is that it's not 20 grams, but rather this is, let's say, 15 grams. Now this was very perplexing for them to even understand what's happening. Suppose that there was an extra mass, then they would have tried to look for something, that okay, fine, instead of 20 it is 25, so 5 grams there should be something else that has that 5 extra grams. But when you have, you know that you have one proton, you know that you have one neutron, and then after that, how is it even possible that the weight is lesser than the total weight of the two particles here? And they did not understand I mean, what exactly it is, and this was called as mass defect. This was called as mass defect. And then when Albert Einstein, when he showed that mass and energy are interconvertible, this is where it was understood that this loss of 5 grams was not loss of 5 grams, but basically this was mass converting into energy. Yes, it actually holds a lot. This was mass converting into energy. So that is where they understood that this nucleus, it actually holds a lot of energy. It holds a lot of energy. Just look at this equation also. All right. So let's say, suppose that we are talking about mass of 1 kg, that you have 1 kg of nucleus. So if you have 1 kg of nucleus, this is 1 into 3 into 10 to the power of 8 squared, meaning 9 into 10 to the power of 16 joules of energy, equivalent to 1 nucleus, 1 kg of nucleus, right? So just imagine the amount of energy that this is packing, this nucleus is packing. So now this can completely unfold new forms of energy for us, right? New form of energy, and completely in one form of energy that was unheard for now. And it can be used in various purposes, right? It can be used in various purposes. Electricity generation can happen through this energy. So we understood all this, and what did we do next? We dropped an atom bomb. So the very first thing that we did after understanding all the things that nuclear energy could do was to drop an atom bomb, and then later realize that, oh, we could also have used it for electricity generation. So unfortunately, Japan had to suffer. So, but this is where basically we understood what nuclear energy is and what the power of nuclear energy is. And this is basically the nuclear binding energy, the energy with which the nucleus is binding the neutrons and protons together. That energy is called as nuclear binding energy. And the force equivalent to it is called as the strong nuclear force. The force corresponding to this is called as the strong nuclear force. So this basically is the force that binds protons and neutrons together inside a nucleus. All right. So that is called as the strong nuclear force. So that's how basically the thing started, and this is where we understood the amount of energy that it holds. And then we saw that there are various ways in which we can get this energy. There are various ways to get this energy, and that could be through either through radioactivity, through nuclear fission, or through nuclear fusion. So that's the next topic that we have to discuss. But let's take a break here. So these were the basic. So basically, uh, when we talk about if you're talking about this, basically what we are saying is that, let's say if you have one proton and one neutron, and if this one proton and neutron, if it is coming together inside a nucleus, then the what will happen is that it will lose some mass. While it comes together, it loses some mass, and that mass basically that is losing, it is not really losing that mass, but rather this mass is converting into energy to make this happen. To make this happen, that all these are coming together inside the nucleus. To facilitate this, some mass will convert into energy, and that energy will be used for something like this to happen. So this is what's happening here. And same actually also applies if let's say some particle is going out. That if, let's say, a nucleus is going out of the if sorry a neutron is going out of the nucleus, in that also you need energy, because this is able to bind the nucleus or bind the nuclear particles very strongly. So you need that extra energy so that you can get it out. So that energy basically is what we see as the nuclear binding energy. How can we define nuclear binding energy? You can simply say that the energy with which the nucleus binds the protons and neutrons inside it is called as the nuclear binding energy. So let me just write it. The nucleus binds protons and neutrons together inside the nucleus, is the nucleus binding energy. Recap: atomic number and mass number. So atomic number basically is the number of protons inside the nucleus, the number of protons, and mass number is the number of neutrons plus number of protons. So sum of protons and neutrons will be called as mass number. Was mass defect due to nuclear fusion or fission or radioactivity? Actually, none of the three. Basically, when we say mass defect is simply when you have to supply some energy for some work to happen. So that is the concept from where we are deriving it. That if you are trying to bring the protons and neutrons together, you need to do some work for that to happen, and that's the extra amount of energy. So that conversion of mass into energy is coming from the concept of work and energy, rather than fission, fusion, or radioactivity. Work energy concept that I just described. Talking about different elements which have the same mass number. So that will be called as isobar. So for example, let's say carbon 14 and nitrogen 14. They will be called as isobars because mass number of both are same, but atomic number are different, and hence they are different uh, elements. Energy losses, that's the energy. Bhagya, I'm not sure what your question is. Can you write your question, mention your question again? So nuclear binding energy is the strong nuclear force. Yes, you can say that strong nuclear force is corresponding to nuclear binding energy. That mass defect is equal to binding energy? Not entirely, because binding energy basically is very strong energy, and mass defect becomes a part of it. How protons and neutrons increase and decrease? We'll discuss that in radioactivity. Just wait for some time. Do we need to remember mass of proton, electron? No, we don't. Does E is equal to mc squared means that E is loss of energy? No, it does not always mean that it is loss of energy. We are just saying that it is an equivalent amount of energy corresponding to certain mass. So it's not always that it will be equivalent to only loss of energy. Do we need to remember periodic table? Not for UPSC, not at all. Incorrect. There have been certain scientists, and some of the scientists have been of Indian origin scientists only, who have basically raised certain questions with regards to special relativity. Uh, but that's way beyond what we are actually discussing here. Of protons, electrons, I have some network issues. No, I'm saying that you don't have to. You don't really have to. That's for your reference that it was written there. So that otherwise, I don't think that they are going to ask you the mass of electrons or protons. Remembering periodic table, but I don't think it is of any significance for us for our prelims and mains examination. Right. So let's move on. So what we discussed is that there are three ways in which this energy that we are talking about, this huge amount of nuclear energy, there are three ways in which we can get this energy. Either we get this through radioactivity, or we can get this through nuclear fission, or we can get this through nuclear fusion. So we'll try to understand all these three one by one. First is radioactivity. So about radioactivity, basically what we are saying is that any unstable nucleus undergoes a decay, and this is referred to as radioactive decay. Now, first and foremost, when we say unstable nucleus, what is the meaning of unstable nucleus? How do we see that any nucleus becomes unstable? So there are basically two ways in which any nucleus can become unstable. First way could be when the nucleus becomes heavy. All right. Basically, meaning when the number of protons is very high. All right. When the number of protons is very high, that is when the nucleus becomes very heavy, and that is one of the ways in which it can become unstable. The second way in which it can become unstable is that if number of protons is not equal to number of neutrons. All right, this is the second way. And if we want, we can define a third way also, although not necessarily, but this is when the nucleus has extra energy. So in these three ways, we can say that this is when any nucleus can become unstable. So first is when the nucleus becomes very heavy. When the nucleus becomes very heavy. So when the nucleus becomes very heavy, this is where we see something called as alpha decay. All right. This is where we see something called as alpha decay. So this is what alpha decay is. Second is when we are saying that this basically where the number of protons and neutrons are not equal. So when the protons and neutron numbers are not equal, this is what is also called as beta decay. This is called as beta decay. This is called as alpha decay. And the third one, where you see that this basically happens, that when the nucleus has extra amount of energy, this is where we have something called as gamma decay. This is called as gamma decay. So in this manner, there are these three ways in which radioactivity can happen. So radioactivity is nothing but an unstable nucleus basically losing some energy or losing some particles. So that is called as radioactivity. So alpha, beta and gamma decay. So alpha decay happens when the nucleus becomes very heavy. Now understand the basics of what's happening here one by one. So first is alpha decay. So in case of alpha decay, what we are saying is that when the nucleus becomes very heavy, this is where alpha decay can happen. Now when it becomes heavy, obviously the number of protons is very high. If the number of protons is very high, it simply means that the repulsion, the force of repulsion between them is very strong now. And there comes a point when the force of repulsion can become so strong then that now this strong nuclear force is not strong enough to hold it anymore. All right. So that is where we see that some of the nuclear particles may come out of the nucleus. That is called as alpha decay. And it only happens, that's why it happens in heavy nucleus. Because at the one hand, we know that obviously the force of repulsion is increasing. The second factor here is also that the size of the nucleus does not increase in the same proportion as the number of protons and neutrons is increasing. It increases as a cube root of it. So the size of nucleus is basically proportional to the cube root of the number of protons or neutrons. So that's why, so basically means that if the number of these particles is 1, the size is 1. If the number of these particles, if it becomes 8, then only the size becomes 2. When the number of these particles becomes 27, then only the size becomes 3, and so on. So size is not increasing in that ratio, but the number of particles keep on increasing, and that increases the instability inside the nucleus. Just imagine a classroom. That here right now, let's say you are sitting in an online classroom, so it's different. But suppose that if you were in an offline classroom, which has a capacity of 100 students, right? So in that, let's say you are sitting and there are 80 students in the evening batch, then in that case, you can very easily sit in that capacity of 100. But suppose that then I say that I don't want to teach the same things twice. So I want the morning batch students also to come in and sit in the same class. And there are, let's say, 50 students in the morning class. So now there are 130 students who have to sit in this classroom of capacity just 100. So it might become difficult that you might have to somehow adjust to this new reality. And then suppose that I say that, oh, the evening sorry the weekend classes are too big. I also want the weekend batch students also to sit in the same evening class. And then let's say there are 50 more students who come and sit. So then there are 180 students in a capacity of just 100. So obviously this is not something that you are going to accept, and then you will be the ones to rebel, and you'll throw out all the students who do not belong to this batch. So this is precisely what is happening in alpha decay, that the number of particles keep on increasing, the size of the nucleus does not increase in the same ratio, and hence we see that some of the particles will keep coming out of this nucleus. This is what happens in alpha decay. So in case of alpha decay, that's why the mass number of the product nucleus is 4 less than that of the decaying nucleus, while the atomic number is decreased by 2. So what basically is happening is, if you look at this picture, from 240 this decreased to 236, minus 4. From 94 it decreased to minus decreased to 92, that is minus 2. So that's why it basically has decreased by 4 and 2. So 4 and 2 decreasing means what? How many protons have decreased and how many neutrons have decreased? 2 and 2. Yes, 2 and 2. 2 protons and 2 neutrons. That is why this is decreasing by 4, because this is what? This is P plus N. and this is what? This is only p. So p plus n is 4 and p is equal to 2. So that's why n is equal to 2 also. A CSAT question basically for you. So this is basically what is decreasing, and this is what alpha particle is, which is equivalent to the helium nucleus, right? It is equivalent to the helium nucleus. So basically in alpha decay, what's happening is that out of this nucleus, one helium nucleus, something equivalent to helium nucleus, is coming out of this heavy particle, so that it can become more stable, relatively more stable compared to what it is right now. So that's why alpha decay is something that is observed in heavy nuclei. It is something that is observed in heavy nuclei and not in the lighter ones. So that is what becomes alpha decay. Then after this, we have beta decay. Now, in case of beta decay, what I told you is that this happens when the number of protons and number of neutrons is not the same. So, example for let's say for us, the first one is carbon 14. Now, in case of carbon 14, do you know how many protons and how many neutrons? How many protons in carbon 14 and how many neutrons in carbon 14? 6 and 8. That's why it is becoming 14, right? It is 6 and 8. For stability, what do you need? For stability, how many protons and how many neutrons so that it becomes stable? Neutrons is not the same. Now a rearrangement will happen in a manner that the number now becomes equal. So this is 14. This will also remain 14. Just that the rearrangement will happen in a manner that, as you see here, that there is one extra proton and there is decrease in the number of neutrons in carbon 14, and that's why that it becomes what? It becomes nitrogen 15, which has 7 protons and 7 neutrons. So so that's why now carbon basically changes to nitrogen. It changes to nitrogen. It will not remain carbon anymore. And this already is an unstable carbon because the number of protons and neutrons is not the same. So that's why it is unstable. So it will try to gain that stability. And to gain that stability, we see that there is one extra proton and one less neutron. Now, does this mean that there is a proton coming from somewhere outside? How are we getting this extra proton? There's something weird that happens inside this nucleus, and that's the conversion of a neutron into proton. So that's why the number of neutrons is decreasing by 1 and the number of protons is increasing by 1. So there is a rearrangement, a nuclear rearrangement that happens inside the nucleus, and that basically leads to this kind of change. So ultimately, you have to just know one thing, that beta decay happens when the number of protons is not equal to number of neutrons, and this can happen in both heavy and light elements. It can happen in both heavy and lightweight elements. So there is no hard and fast rule. So for example, in alpha decay, we know that it only happens when you have a very bulky nucleus. But here, wherever the number of protons and neutrons is not the same, it can happen. So whether it is a lightweight nucleus, whether it is a heavy nucleus, doesn't matter. It can happen anywhere. So that is what we see with beta decay. All right, that is what we see with beta decay. So this is the case of carbon 14 changing to nitrogen 14, as you can see here in the picture, that carbon 14 has changed to nitrogen 14. And there is another scenario where carbon 10 can change to boron 10, because in carbon 10, what again happens is number of protons will always remain the same, 6. Number of neutrons now is just 4. That's why 10. Correct? So for the number to be stable, this 10 needs to be 5 plus 5. Why am I writing 6? This needs to be 5 plus 5, and this 5 plus 5 basically is boron 10. So from carbon 10 we have changed to boron 10, and what is happening here is that number of protons is decreasing by 1 and number of neutrons is increasing by 1, meaning that this time a proton would convert into a neutron for making this stability take place. So that's what's happening inside this. So you do not need to know the equations and all these things I've shown you. It's just basically to give you the context of what is happening. But ultimately, just remember these 2 points, that number of protons and neutrons are not equal, and it can happen in both an light and heavy nucleus. Just that wherever the numbers are not equal, beta decay will take place. That's it. Then we have gamma decay. Now, in case of gamma decay, what we are basically saying is that this nucleus has extra energy. It has more energy than it should have. All right, it has more energy than it should have, and that is where gamma decay would take place. So what we see is that if you see this, sorry, if you, let's say, when we are talking about any alpha or beta decay, when we are talking about any alpha or beta decay, in both the cases, basically what is happening is we know that we get an unstable nucleus initially, which is getting to stability, but this unstable nucleus also has extra energy. It has extra energy after alpha or beta decay. That extra energy is lost by the nucleus. It basically loses that extra energy so that it can settle down into its ground state, into its stable state. So that extra energy basically is coming out as gamma rays or gamma radiation or gamma particles, and that's why it is called as gamma decay. So when a nucleus is in an excited state, spontaneously decays into ground state, a photon is emitted. Photon basically are energy particles, is emitted with energy equal to the difference between the two energy levels. So that extra energy is being released. All right, that extra energy is being released, and that's why typically we see that after alpha or beta decay, we see that gamma decay would also take place, and this is where the things will uh, now come down to the ground state. So basically what we see is that from an excited state, so excited, why? Because it has extra energy. From excited state we come down to ground state. So excited state basically has extra energy, and here there is no extra energy. So this is something called as gamma decay. So overall, when it comes to alpha, beta, and gamma radiations, we see that alpha radiations have the least amount of energy. They have the least amount of energy. So that's why even if we have a thin sheet of paper, it will be able to stop the alpha radiations. Beta radiations have higher energy. So that's why we need a thin sheet of metal like aluminium so that we can stop beta. And in case of gamma radiation, we see that gamma radiation basically has extra energy, has very high energy. Same goes for X-rays as well. So we need a thick sheet of lead to stop gamma radiation or even X-rays for that matter. And neutrons, compared to all of them, has even higher energy, and that's why you need a sheet of concrete or steel to stop it. So that's why it's not that easy that we'll be able to stop that radiation. So uh, overall we see that all these are the different types of radiations or different types of particles as a part of radioactivity. So just remember the summary of it, the first slide that we had discussed, that when you have very heavy nucleus, this is where alpha decay will happen. What is alpha decay? Just that helium nucleus is coming out of the particle, is coming out of the out of the nucleus. Then after that we have beta decay. In beta decay, when the number of protons and neutrons are not equal, this is where beta decay happens, and it can happen in any element where number of protons and neutrons is not equal. The third one is gamma decay, where all the extra energy that a nucleus has after alpha or beta decay, that extra energy will be lost. And this is how nuclear fission works. So nuclear fission, this is how gamma decay works. So that is basically what radioactivity is. Now, when it comes to nuclear fission, which is the next type of uh, energy or nuclear process, fission. The meaning of fission, do you know what is the meaning of the word fission? The dictionary meaning of the English word fission? Yeah, to break, to split. Correct. To fission in a manner means to break. So, which is precisely what happens here, that the nucleus basically breaks into two parts. Until now, what we knew is that there are some particles coming out. It is just losing a couple of particles or losing some energy, etc. That's it. But here, what we are saying is that this nucleus is basically breaking into two parts. All right, it is breaking into two parts. So that is called as, that's why it is called as nuclear fission. That when you have any nucleus that breaks into two or more nuclear particles or two or more nuclei, then in that case it is called as nuclear fission. This is called as nuclear fission. So if you look at this particular figure, this is basically what happens with nuclear fission, that in case of nuclear fission we have this uranium 235. Now what you see is, if you see what's happening here, is that we have uranium 235 in which one extra neutron is being bombarded. This extra neutron goes and sticks to the surface of uranium 235, and then it becomes uranium 236, which is unstable. And now this breaks into two parts. Because it was unstable, it just breaks into two parts, and while releasing a lot of energy. So this is basically what is being shown here. Now, when it comes to nuclear fission, fission means, as I told you, fission means to break, and that's why it is breaking. So what we are doing is that we are taking uranium 235. Now this uranium 235 is pretty stable. Okay, this is very stable nucleus. It does go undergo radioactivity, but it will not break. Okay, it will not break. It will just keep undergoing radioactivity. But when there is an extra neutron bombarded towards it, this neutron goes and sticks to the surface of uranium 235, making it uranium 236. That's why uranium 236, because mass number is increasing. Why is the mass number increasing? Because now you have an extra neutron. That's why the mass number is increasing. And that is why the atomic number is not increasing, because number of protons is remaining the same, but number of neutrons is increasing. That's why 235 becomes 236. And this 236 is very highly unstable, and it breaks into two parts. All right, so breaks into two parts, barium and krypton. So you have krypton here and you have barium. So it breaks into two parts. Now, what we basically see is that in this particular scenario, enormous amount of energy is produced, a huge amount of energy. This energy basically comes from the kinetic energy of the moving particles. Kinetic energy of moving particles plus gamma radiations or gamma particles, let's say. So that is where all this energy is coming from. And apart from that, there are three extra neutrons. As you can see here, there are three extra neutrons which are still left. there are three extra neutrons. So these three extra neutrons will go on and keep on bombarding more particles. So this is not going to stop here. So until now, so basically, and how these three extra neutrons, just do the simple mathematics. What you see is that you have 236 here. On this side, you have 236. This 236 is dividing into 92 and 141. So how much is 92 plus 141? It is 233. So that's why you are left with three more neutrons, right? You're left with three more neutrons, and these are the three neutrons that we have right here. All right, these are the three neutrons that we have right here. So now these three neutrons will go on and bombard more of these neutrons. Sorry, more of these uh, uranium. So from here, basically three more will be produced. From here, three more will be produced. From here, three more will be produced. From here, again, three more will be produced like this. From here, again, three more will be produced. And this will basically keep happening. This will keep happening, and that's why, in a manner, a chain reaction is set up here. Because you have to understand that when these reactions are happening, it's not that you have just one nucleus of uranium 235. Even if you have 1 gram of uranium 235, then in that 1 gram of uranium 235, you will have at least 10 to the power of 22 such particles, 10 to the power of 22 such particles of in just 1 gram of uranium. So imagine the amount of uh, nucleus that is available in front of, or in front of these extra neutrons. So they'll just keep on bombarding, and that's why a chain reaction will be set up here. And this chain reaction can become very dangerous because enormous amount of energy is being produced at each and every step. So that's why, with the number of free neutrons that you have, it will just keep on increasing. From 1 you had 3 neutrons, from 3 you have 9, from 9 you have 27, from 27 you have 81, 243, 729, and so on. So it just keeps on increasing in this ratio, and it has all these uranium nuclei available in front of them. So they will just lead to a chain reaction. They'll keep on bombarding newer uranium nuclei, and they will just keep on increasing in number. And that's why huge amount of energy can be released here, and this is the energy that we will have to control. We will have to find a way to control this energy. Otherwise, this energy, if you control this energy, all right, if you control this energy, then you produce electricity from here. If you don't control this energy, you get an atom bomb out of it. So the same process can make a nuclear weapon for you, and the same process can also help you uh, get energy, generate electricity, and probably solve the problem of energy for the world. So that's basically what's happening in this particular scenario. So what we know is that this is something that we see, that a chain reaction is set up. All right, so I'll just write here, a chain reaction is set up due to the available extra neutrons bombarding the uranium 235 nuclei. All right, so a chain reaction is set up because of that. It's important to control the chain reaction for energy generation. If not controlled, it could lead to creation of an atom bomb. So that is why we see that this has happened, and all these things happen within seconds. It's not that it's taking some time. It will all happen within seconds, and within seconds it can just destroy a place if at all the reaction is not controlled. So we need to control that reaction, and to control the reaction, there is something that we have called as critical mass. All right, there's something called as critical mass. Now this critical mass basically is that mass of any material. Critical mass is that mass of any material at which you can set up a controlled chain reaction. That mass at which you can set up a controlled chain reaction is called as critical mass. So critical mass basically is the minimum mass, or let's say that mass of uranium 235 in this particular case, at which you can set up a controlled chain reaction. So critical mass becomes very very crucial, because if you are below critical mass, then this reaction will stop quickly. If you are below this critical mass, the reaction stops quickly. And if you are above this critical mass, the reaction can go uncontrolled very quickly. The reaction can go uncontrolled very quickly if you are above critical mass. And if you are below critical mass, the reaction can stop quickly. There is a factor, I mean, it's not related to your exam at all. There's a factor called as K, and this K has to be 1 in the entire equation of the computation of nuclear energy. There is a factor called as K, and if the K factor is 1, this is what is critical mass, and a controlled chain reaction is set up. If this K is even 0.99, if the value of K is even 0.99, the reaction will stop within seconds, or even couple of minutes. Let's say the reaction will just stop, because K being 0.99 means that you do not have enough neutrons to run the reaction. So reaction stops. If K just increases by 0.01, and if it becomes 1.01, so if just a small increase also happens in K, the rate of reaction can increase by 22,000 times. So just understand the kind of problem that we are talking about, and forget what K is, and we don't really need it. It's not required for your examination. I just want to give you the context of what can happen. That if there is a small increase in this factor, it can lead to the rate of reaction increasing by 22,000 times, and that is uncontrolled chain reaction, and then after that it can lead to a nuclear disaster. So that is why it's very very important that we maintain the critical mass. All right, that we maintain the critical mass, because at critical mass you can set up a continuous chain reaction. At critical mass, at critical mass we can set up controlled chain reaction, a continuously controlled or continuous controlled chain reaction. All right, so that's why critical mass becomes very very crucial. So that's why mass of the fissile material, or that mass of uranium 235 at which we can set up a continuously controlled chain reaction. So let me just write this instead. that mass of uranium 235 at which we can set up a controlled chain reaction. All right, so that's why critical mass becomes one very very important part of nuclear fission. Then after that, there is one more problem with nuclear fission, and that is something to do with the question of enrichment. Now, enrichment is a term that is very often in the news also. That enrichment of uranium is happening in Iran. It was in the news. US was claiming that Iran has achieved 90% enrichment or 85% enrichment. All these kind of things were in the news last year. So, what is enrichment? We need to understand here. Now, there is one problem that we see when we mine uranium. The natural uranium that is mined, it has two isotopes of uranium, uranium 235 and uranium 238. And we discussed about uranium 235, that uranium 235 is used in the chain reaction. Uranium 238 is not usable. I mean, it will keep going and it will keep undergoing radioactivity, but nuclear fission does not happen in uranium 238. Or for that matter, uranium 235 is the only natural element that is capable of undergoing nuclear fission. Apart from uranium 235, there is nothing natural that can undergo nuclear fission. Uranium 238 cannot. It will undergo radioactivity. It will never undergo nuclear fission. Now the problem is that if we have 100% of this natural uranium, in this only 0.7% will be uranium 235, and rest 99.3% is uranium 238. So now understand the problem, that out of this natural uranium, if you have 100 grams of natural uranium that you have mined, in that only 0.7% is uranium 235, and rest 99.3% is uranium 238, which is not of use for us. So then this is where we use a process called as enrichment. Now with this process of enrichment, what we basically do is we try to increase the proportion of uranium 235, the ratio of uranium 235, we try to increase it from, let's say, 0.7% to up to 3 to 5%. So that process is called as enrichment. So enrichment basically is when we convert some of uranium 238 to uranium 235. Right, we convert some of uranium 238 to uranium 235. So in that case, basically this 0.7 increases to 3 to 5%. This is the kind of increase that we want. Now there's a question, why 3 to 5%? Why not 20? Why not 100? Convert 100% of uranium 238 to 235. Have more fuel available with you. Why don't we do that? The reason is, as you keep on increasing the enrichment levels, this nucleus becomes very unstable, and making a nuclear weapon out of it becomes easier. So that's why there is an international understanding that nobody or no country will do an enrichment that goes beyond 5%. Because if you are going beyond 5%, it means that you are not going to use it for energy anymore. You are creating weapons. And that's why the countries are not allowed to go beyond 5%. Now, this is what comes in the news from time to time. Last year, the US had claimed that Iran now has reached almost 85% enrichment. 85% enrichment. And 85% enrichment simply means that they are creating weapons. They are not going to use it for peaceful purposes or electricity generation, but rather they are going to create weapons. So that's why enrichment always is done only up to 3 to 5%. Beyond 5%, chances are that you're not using it for electricity production anymore. You're going to use it for creation of weapons. So that is the reason why enrichment as a process becomes very crucial in this particular scenario. So that's why there are two problems that we are facing. One, that we need to define the critical mass. Second, we need to define the enrichment levels. If we have done both, we'll be able to get energy, or we'll be able to generate electricity out of it. Any questions? If you have any questions until now from radioactivity or from nuclear fission, whatever we discussed until now, anyone? How neutron has high energy? See, it's just an intrinsic property of the neutron that it has a lot of energy, and it's because of the internal weak forces, the weak force particles that we have inside, that basically creates that energy. But to explain the answer to your question, I'll have to go to particle physics. That's not possible here. How much time it takes for the reactions to end? It depends on how many particles are there in the reaction, the participating reaction. The reaction does not go on for a very long time because it's a very you can say sudden burst of energy that happens. So within seconds the reaction stops. If you I mean, obviously, if we are not creating an artificially, if we are not creating this chain reaction, otherwise it will just take seconds. What is the process of enrichment? So enrichment is nothing but when we are converting some of uranium 238 to uranium 235. So we are increasing the percentage of uranium 235 in the mixture of 235 to 238. How to convert? See, the conversion basically is done through radiations. That extra amount of radiations are uh, made or made incident on the nuclear particles, and that is where we see that internal conversions happen. Energy to cross this entire concrete particles. uh, that's why it takes time. Gamma decay. So in case of gamma decay, basically what we are saying is that the other nuclear processes like alpha decay or beta decay, they, once they are done, the nucleus has more energy than nucleus should have. So that extra energy that is lost by nucleus so that it can become stable again, that basically is called as gamma decay. 3 to 5% is not understood. Basically what we are saying is that we have only 0.7% of uranium 235. That basically will be increased to 3 to 5% of uranium 235 in the mixture, because you need uranium 235 for electricity generation. With only 0.7%, it's not enough for getting the amount of energy that we need to get from there, and that is why this will be done. Kindly explain how uranium 235 is stable and uranium 236 is unstable. See, these are relative terms saying that these are stable and unstable. Just that uh, there is no room for that extra neutron in the structure, in the chemical structure of, or rather the nuclear structure of uranium 235. And that's why when the extra neutron comes into the picture, it completely rearranges the nuclear structure and that becomes very unstable. With more enrichment, does the nucleus become unstable? Precisely, yes, it does. What is being converted from uranium 238 to 235? Uranium 238 itself is being created, converted to uranium 235. Do we have to learn all these numbers and equations? No, we don't. Please summarize everything which you taught after the break. It's an unfair request. I would rather have you go back and just revise from the recorded lectures rather after the class. Are X-rays radioactive? No. X-rays are not, we can't say that they are radioactive. They basically have their origin in the electrons and not inside the nucleus. How thorium is used, thorium will come to it. Just wait for some time. How a neutron is bombarded in uranium-235 in a bomb, like will it explode when it touches the ground? It's not about touching the ground, it's about the nuclear reaction that we have created, and these will basically be triggered. All right, we'll be triggering it by the bombardment of an extra neutron, and that basically, that trigger will basically lead to the nuclear explosion. Do we have sigma energies also apart from alpha, beta, gamma? But sigma is not really related to your nuclear energy, it's more related to your bonding, the basically the chemical structures. Where beta and gamma decays are stored. I mean, we don't store it. Why would we store it? When we convert it from 0.7 to 3 to 5%, it doesn't have any negative effects. No, it doesn't. It helps us in producing more energy or more electricity out of it. What is the problem if you enrich above 5%? The nucleus starts becoming unstable. It becomes very easy for you to make a nuclear weapon out of it. Can you please end the class at 8:15 today? Wouldn't be possible. We'll really have to go a bit beyond that, but almost will be done by 8:20, 25, and then it will be about questions. If you, for some reason, are going to miss it, please go through the recorded lectures of the last 15 minutes whenever you get time. Why uranium 235 can't be enriched above 5%? I'm saying we can. I'm saying that it becomes unstable. We don't want to. The countries are prohibited from doing that. Please, every day I'm asking something, that when you type a question, type the question once. Type the question once. Please do that. And Mainam, you are somebody who does that every day, and I'm taking your reference only every day, that you type the same question. I see your question 1, 2, 3, 4, 5, 6, 7, 8, 9 times on just this side panel. So just imagine what happens with others. They, their questions will be missed. Why do you have to type 10 times the same question? And I have already answered your question. After that, you are asking the same question 10 times. Harmful effects of decayed nuclear weapons. We'll discuss this towards the later half of our discussion. If not stored, these rays can cause damage. So it's not about storing, but rather prohibiting, because that's why we talked about those uh, uh, concrete walls or the steel walls, etc. That is how we case them, and we'll discuss about that a little later. Why fission does not break into three parts? It can. There are possibilities that it can, but generally speaking, see, every uh, many of things that happen, they are interesting in their properties. It's not that there is a particular reason for that. We just see that there are rearrangements that happen, and these rearrangements lead to this kind of a scenario. What is the percentage of uranium enrichment required for nuclear research reactor? The same. I mean, 3 to 5%. Everywhere it is the same. Explain difference between fission and fusion. We have not started fusion. Just wait here. In alpha decay, why protons are only 6, not 5 or 7? We never said that. I said that protons are only 2 because it's helium. Still confusing critical mass. So critical mass basically is the required amount of uranium 235 that can undergo a continuous chain reaction. So for example, let's say we need 10 kg of uranium 235 to run a reactor. So that 10 kg of uranium will be called as critical mass. If we need 15 kg to run a reactor, 15 kg will be called as critical mass. All right. So let's move to the next topic, and our next topic is nuclear fusion. Now, in case of nuclear fusion, fusion means to join, right? Fusion means to join. And that is why what's happening here is that there are two particles that are joining together or fusing together, and this is called as nuclear fusion, right? This is basically what we say is nuclear fusion. So nuclear fusion is when these two particles join together, and nuclear fission is when particles break. Now, when particles break, they release a lot of energy. Even when particles join, even then they release a lot of energy. There is a reason for that. I'm not going into the details. It's very technical for you to know. But nuclear fusion also will lead to release of energy. And release of energy in case of nuclear fusion is much more as compared to nuclear fission. In case of nuclear fission, the amount of energy that we release is less, and in nuclear fusion, it's way more. And this nuclear fusion precisely is also the source of energy of the sun. The energy that we are getting from the sun, the heat and the light and radiations, etc., they're all because of nuclear fusion. It's all because of nuclear fusion. So just imagine that we are talking about a kind of reaction that is basically running the sun, correct? So that's why it's a huge amount of energy. It's huge amount of energy, and from very small particles we are actually able to get this much of energy. So in nuclear fusion, there are two lightweight nuclear fuels that combine to form nucleus of a heavier element. So now in this particular scenario, what we basically see is that nuclear fusion, there will be the nucleus of hydrogen, and nuclei of hydrogen will join together. Hydrogen converts into helium by joining, while releasing a lot of energy and again neutrons. So this is basically what we see in case of nuclear fusion. Now if you see this, this is what happens inside the sun. This is what happens inside the core of the sun, that we have hydrogen that combines together, and this hydrogen, while combining, creates deuterium. This deuterium will combine with more of hydrogen to form helium 3. Now helium 3 of course will be unstable. Helium 3 is unstable because number of protons and neutrons is not the same, so it is very unstable. And this helium 3, that's why, will combine with more of itself to form helium 4, which is the stable helium. So ultimately what has happened is that this chain reaction has led to hydrogen forming helium, right? Hydrogen basically is converting into helium while releasing a lot of energy. Hydrogen is converting into helium while releasing a lot of energy, and this is happening in nuclear fusion. Now in this kind of fusion, or in this nuclear fusion also, the amount of energy that is released is very, very high. Very huge amount of energy is released here. Now this is also because this process is not that easy. Nuclear fission as compared to nuclear fusion is a lot easier. All right, nuclear fission as compared to nuclear fusion is a lot easier process and easier to implement process for even us. Nuclear fusion, on the other hand, we need very, very specific conditions. We need very specific conditions, and only under these specific conditions nuclear fusion is possible. Otherwise nuclear fusion is not possible. So that's why we need extreme conditions. And what are these extreme conditions? Something that we have inside the sun: extremely high temperature, extremely high temperature, extremely high pressure, very strong magnetic field. Extremely high temperature, extremely high pressure, very strong magnetic field. Under these conditions we see that nuclear fusion becomes possible. Otherwise, if you don't have these conditions, nuclear fusion is not possible. So that's why getting this is very, very difficult. But at the same time, if we can, then the amount of energy that we can produce is huge. Now for nuclear fusion, that's why ultimately what we need is that it is necessary for us to bring two nuclei so close that the nuclear forces between them become active, and then it will make them stick together. And that's why we need these extreme conditions to make them stick together. Otherwise they are stable enough, they're not unstable. You cannot say that hydrogen is unstable, right? In case of uranium 235, we were saying that uranium 235 is anyway radioactive. Uranium 236 becomes very highly unstable and it breaks. But in case of hydrogen, hydrogen is not unstable, hydrogen is fairly stable. So then also it goes under and it can undergo nuclear fusion. But for that you need these specific conditions under which it can stick together. And only if it can stick together and form helium, that is where it releases a lot of energy, and this becomes nuclear fusion. Now for this nuclear fusion to occur, there are two approaches that we use. There are two ways in which we try to make this work, and these two ways are called as confinement approaches. One called as magnetic confinement, another one called as inertial confinement. So magnetic confinement is where we use very strong magnetic fields for activating nuclear fusion. For making nuclear fusion happen, we use very strong magnetic fields. That is called as magnetic confinement. And on the other hand, we have inertial confinement, where we use very powerful lasers. We use very powerful lasers, and through lasers we provide that energy so that we can bring these particles together. We can bring these particles close so that nuclear forces between them can be activated. So this is basically what we try to do uh, in case of inertial confinement. So magnetic confinement is something that is being also tried in ITER, International Thermonuclear Experimental Reactor. This is something that is using magnetic confinement. Now, with magnetic confinement, they basically have been trying to uh, experimentally succeed in nuclear fusion. Now, experimentally, have they succeeded? The answer is yes. But they still haven't been able to reach a level where commercial production of nuclear fusion can be made possible. And this is where the complexities start to increase, where we want that we can actually make the use of magnetic confinement to make commercial use of nuclear fusion. Nuclear fusion has been made possible. Experimentally, we have succeeded, but we haven't succeeded in a manner that electricity supply can happen through nuclear fusion. We haven't been able to do that. So in ITER, they are using something, again, something that will be in news a lot of times, called as tokamak. Tokamak. Now, what is tokamak? Tokamak basically is a toroidal shaped magnetic coil. What is toroidal shape? Do you know? What is the a toroidal shape? Toroidal shape is just like, have you eaten donut? Have you tried eating donut? So the shape of the donut basically is the toroidal shape, or in a manner you can say a tire. If you see a tire, how you have a tube tire, that it is like a ring, correct? It's like a ring. So that tire shape or the shape of the donut is called as toroid. All right, this is called as the toroid shape. Yes, like medu vada. That's a perfect example. Yes. So this kind of a shape is called as the toroidal shape. So that kind of a shape, in that shape we have magnetic field, and that magnetic field tries to confine the charged particles or nuclear particles inside it. All right, the nuclear particles inside will be confined with the help of this toroidal shaped magnetic field, and there we try to make it happen. So that is called as the toroidal shape. So toroidal shape. So the name is tokamak. The tokamak comes from a Russian word, so that's why it's not even something that I would be able to pronounce. So from that this tokamak, it basically is a toroidal shaped magnetic field under which we try to confine the plasma or confine the nuclear particles so that nuclear fusion can be made possible. And have we been able to make it possible? Yes. Experimentally, yes, but not at a scale that can be usable in our daily lives. So that is where they have been trying for a very long time now. And then after that, we have the inertial confinement, where we are using powerful lasers or ion beams. The lasers will be used so that they can help them bring these particles together. Now, in this particular scenario, there is something like this which has been in the news in the last 1 year. Why fusion could become a clean energy breakthrough, something that had happened, and news of last year, December, as you can see, December 2022, and then August 7th this year again, where for the second time they were able to get a breakthrough in nuclear fusion. And do you know what this breakthrough was? This breakthrough, if I tell you about the breakthrough, you'll think that why is it even being called as a breakthrough? For the first time, for the first time, the scientists have been able to generate more energy than they consume in the operations of nuclear fusion. Until now, the scenario has been that if they are using 1000 joules of energy, they are able to generate 500 joules of energy out of it. That is why we are saying that it's not commercially viable yet, because you need more energy than you are consuming, right? You need to generate more electricity than the electricity that you are consuming in the operations of making this nuclear fusion work. So until now, with magnetic confinement, we haven't been able to do that. That is why I'm saying that experimentally we have succeeded, but real life scenario we haven't, because we are using a lot more energy to make nuclear fusion work. Now, for the first time last year, the Lawrence Livermore National Lab in the US, they were able to produce more energy from fusion than the laser energy that was used to drive it. Right. So that's why for the first time they were able to get or generate more energy than the energy that they are consuming in the operation. And it's not that it was a huge amount of energy, it was enough energy to just boil a few kettles of water. That's it. So that much amount of extra energy that they were able to produce. And this is the breakthrough that we are talking about, that for the first time at least we could generate more energy than we are consuming. So at least we are heading in the positive direction. And that's why scientists are saying that this is a big breakthrough. And very soon they are saying that the nuclear energy might become a possibility, and that in the next 20 years nuclear fusion would become a possibility. And this is also, I mean, now this has become a meme material, unfortunately. So that we are saying that this energy or nuclear fusion energy is 20 years away, because scientists have been saying that nuclear fusion is 20 years away for the last 50 odd years. So for the last 50 odd years, it has not changed. Still 20 years. So again, when the breakthrough happened, they still again said that 20 years. Just wait for 20 more years. So that's why in the 1980s, it was 20 years away. And in 2023, still 20 years away. But you have to understand that it's not that easy. I mean, making jokes on it is easy for me sitting here. But if I was a part of the experiment, I probably will not be joking about it. So, but it's a big breakthrough. Why? Because for the first time at least we could generate extra energy, and that means that we are moving in the positive direction, and probably in the coming days we'll be able to get better at using nuclear fusion. Now, so we talked about the International Thermonuclear Experimental Reactor. So ITER, something which is located in France, and this is where magnetic confinement is being used. We are using magnetic confinement approaches to make this work, to try and make this work. So it has been apart for a very long time, and ultimately, so aims to demonstrate that it is possible to produce commercial energy from fusion, right? With the help of fusion, we can produce commercial amount of energy. Now, when it comes to ITER, we see that this is something uh, where first it started with the former Soviet Union, okay, USA, European Union, and Japan. These were the first four countries that came together and they started this ITER. And then after that, later we see that countries like India, China, and South Korea, they also joined. So today we see that there are total of 7 members, and these 7 members together are trying to make this work. India also has been a very crucial part of this ITER for the last almost 17-18 years. So that's why we have also been trying, and let's see where it moves. And right now we are just trying to make it happen. Now, coming to the advantages of fusion, that why are we spending so much money on nuclear fusion? Nuclear fission already working for us, but yet there's a lot of money being invested, a lot of money being used in making nuclear fusion work. Why so? The first, just look at some of the advantages that nuclear fusion gives us. First, abundant amount of energy, huge amount of energy. Sun is an example, that just imagine the amount of energy sun is able to produce and give us. So even at a very 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 small scale also we are able to replicate that's happening there. Our energy requirements are done. once nuclear fusion Once nuclear fusion becomes a reality, once it becomes a daily reality or a commercial reality, every other source of energy, every other kind of energy that we are using today, we probably will stop using it. This entire energy chapter that has been of last three sessions will be of just one portion, which is nuclear fusion, because solar energy, wind energy, biothermal bioenergy, geothermal energy will all become irrelevant once we are able to crack how to use nuclear fusion. So abundant amount of energy is what we are expecting. Now, second, the sustainability factor. that we are using hydrogen. Hydrogen is abundantly available, and also at the end of the reaction you get more hydrogen, and that can also be reused. So that's why with nuclear fusion, once a reality, for a very 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 long time we will have enough of energy that will not have to worry about it being spent. So that's why it's another advantage. Obviously no carbon dioxide, these are nuclear reactions, so there is no coal, no petroleum, no hydrocarbon, no carbon. So that's why there is no carbon dioxide being emitted, so becomes very very clean source of energy also. No long lived radioactive waste. Now this is a problem with nuclear fission. This is a problem with nuclear fission. So, in case of nuclear fission, we know that a lot of uranium based wastes or other radioactive elements, etc., they are the waste, they are the byproducts. And that's why this becomes a problem altogether. But in case of nuclear fusion, in case of nuclear fusion, fusion waste, fusion waste is tritium water. Tritium water, basically made out of another isotope of hydrogen. So that tritium water, basically something that we also denote sometimes as T2O. Now tritium water is very unstable and it very quickly converts into normal water. So the waste that we are generating, it's not a long-lived waste, but rather it's a waste that very quickly will just decompose or very quickly just convert into normal water. So that's why the waste that we are generating is not long-lived radioactive waste. It's a safer waste. Limited waste of proliferation. What is proliferation? Anyone who has an idea? The spread, correct? Weaponizing, yes. Spreading of the arms, correct. So basically proliferation, in a manner you can say that we are talking about weaponization, correct. We are talking about weaponization. So the chances that we could weaponize nuclear fusion is less. Remember, we are saying limited, I'm not saying no risk, I'm saying limited risk. So compared to that, weaponizing nuclear fission is easier. We get plutonium as a byproduct. Plutonium can be used to make atom bombs. So that's easier. In this case, what we are producing does not facilitate making hydrogen bomb so easily. Making hydrogen bomb is a completely different process. You cannot reuse this process. But in case of making an atom bomb, it's easier to just use the same electricity generation process. From the byproducts that we are getting from there, we can actually use it for making atom bomb. So that's the difference, and that's why the risk of proliferation here is limited. Then no risk of meltdown. Another problem with nuclear fusion. Sorry, nuclear fission. This is another problem with fission, because there the chances of accidents are higher, because we have very there are various conditions that are maintained, and we'll discuss about that when we go to the nuclear reactors part, when we discuss about all that. So you'll understand that there are a lot of things that's happening there, and that leads to the chances of meltdown, the chances of accidents. But all those scenario uh, will not happen with nuclear fusion. So that's why nuclear fusion gives us another advantage in this scenario. And the cost, once we make it a reality, once we are able to commercialize it, we are able to crack it, after that, because we are using hydrogen and from very small amount of hydrogen a lot of energy is being produced, we'll not have to think about the cost factor. The cost will be drastically smaller as compared to lesser as compared to the other sources of energy that we might potentially use. So that's why nuclear fusion gives us a lot of advantages. There are a lot of different advantages that it might be able to give. Look at this question. This was asked in your 2016 paper. It's a simple question. India is an importer too, not what we have been studying. Look at the first statement. It is talking about can use thorium in place of uranium. We have not read about thorium. Uranium we know is related to fission. So how can the answer be A? It can't be. It can attain global role in satellite navigation. I want to understand why would you mark this answer? How is it anywhere related to what we are discussing? It can drastically improve the efficiency of fission reactors. Look at this. It is talking about fission. It is not talking about fusion. So this is wrong. It can build fusion reactors for power generation. That's it. There's only one option out of the four where you even have the required keyword. The other options does not even have the keyword required. So that's why the correct answer is D. This was an easy question. Okay, so let's stop here because it's a big topic. So we'll start from here. So we'll discuss about, so basically you can say nuclear science is done and nuclear technology is what will start tomorrow. So almost 1 hour to 1.5 hours we are left with, and then we'll move on to our next chapter, which is biotechnology. All right. So we'll discuss this and we'll discuss about biotechnology in tomorrow's class. Meanwhile, if you have any question with regards to whatever we discussed in the last half an hour or so, please let me know, and then we shall end the class for today. This question was asked in 2016. Meltdown. Meltdown basically is nuclear accident, or let's say meltdown of the reactor means that when reactor starts to leak the nuclear material. So that is called as meltdown. What is the point of cost? So cost, basically what I was saying is that once we are able to start using hydrogen for nuclear fusion, the cost will drastically drop down, because with very small amount of hydrogen a lot of electricity could be generated. Discharge of radioactive water in the Fukushima nuclear power plant. Yes, that is something that has been in the controversy in the last year, because Japan decided that they'll release nuclear water into the Pacific. They are saying that it's completely safe. They have completely, uh, they already have treated this water and then only they are releasing it. But uh, when it comes to nuclear fission specifically, the chances of it having radioactive elements in it, radioactive material in it, is very high. And that is what has a lot of people worried, that uh, even if Japan says that it's completely safe and it has completely been treated and all those things, still it's very, very difficult for somebody to even uh, believe that something like this could even happen. And that's why we see that there is so much of controversy around it. Inertial confinement, just that when we are using lasers, when we are using lasers to confine the particles together so that nuclear reaction could take place between them. Once briefly explain what is nuclear fission and fusion. Simple. Fission means to break. So when a big particle breaks into two parts, it is nuclear fission. So that is what is happening with uranium 235. That uranium 235 bombarded with a neutron becomes uranium 236. Uranium 236 is very bulky and very unstable, breaks into two parts. That is nuclear fission while releasing a lot of energy. Nuclear fusion means to join, right? So that's why this is where two nuclei of hydrogen will join together, and while joining they release a lot of energy. This is called as nuclear fusion. Why hydrogen bomb is more powerful than atomic bomb? Because hydrogen in general packs a lot of power compared to anything else, and that's why you'll see that everywhere, even in energy production, we want hydrogen. We want hydrogen everywhere, whether to run vehicles or do anything. And that's why when nuclear fusion is used, it will have a lot more power as compared to uranium. Leaderboard. Okay, leaderboard. This is the leaderboard for today.